4, 3 to negative 1. That's another way to say it. But that's not very useful.
Well,
I to the 1, 4.
I mean, I could do stuff like I squared. What's I squared?
-1.
Negative 1. That's easy enough. So if I can raise I to a power, and I can raise a number to a power, I should be able to raise I to the 1/2 power. And actually get something more useful than, well, it's a square root. Yeah, that's more like a definition. This should be the only one that is a definition. And then I should be able to do math to it and figure out answers for every power, addition, division, whatever. So part of what we're going to do today is we're going to figure out how to do that. Something like the cube root of I, you can actually do pretty easily. Believe it or not.
Well, because
So you guys help me out.
cube root of -1 is...
No, it's not negative 1. Right? What's I cubed? Somebody remember? I squared is negative 1. Yeah, I cubed would be that times another I. So it's negative I. So what is negative I cubed? Just move the negative. Where is that cool? So what's the cube root of I then? Take the cube root of both sides. Negative I. Cool. So we can figure out like the cube root of I like by manipulating things with this. You can't do anything like that with the square root of I. You just can't. But square root of I actually comes out to be a decently normal little thing. So we're going to actually figure it out today based off of what we learned. Okay.
So the cube root and the cube of I is negative.
Yeah, it's interesting. So I cubed is negative I. And we just figured out that the cube root of I is...
That's kind of cool.
Negative I, yeah, it's kind of nifty actually. Okay. So that's what we're working towards. Where we ended up last time. So we have, I can rewrite a complex number in what form?
Polar.
Lovely. What exactly is it? All right, so it's given to me as a plus bi. How can I rewrite that?
R times cos.
Cool, right? And then again, it's because we're imposing the idea of polar coordinates. If I make an imaginary axis, I can kind of see, will the math of polar coordinates, will the math involved there help me do stuff with complex numbers? Well, it will. Today it'll help us do that. So we're able to do things with complex numbers if we rewrite them in a different form than I ever could hope to do. I can't do anything with this. There's nothing I can do with that. It's not going to go anywhere. But if I rewrite it in a different form and use more geometric arguments to it, right? So this is kind of like making it more visual, more of a, I can see it. I can see the complex number. And the math behind this allows us to do more with these things. So what we did yesterday was a little lame. I don't know if you guys picked up on it, but it was the first step in getting towards something that's a lot more powerful. So what we did yesterday was, okay, what if I had two of these things and I multiply them together?
Yep.
What's the basic idea of what happens?
R1 times R2
times
cosine.
theta 1 theta 2.
Yeah, so it's pretty simple to prove this. You just brute force multiply those bad things out, and then you collect stuff for trig identities, and it cuts down to here pretty quickly.
Yep.
So obviously, I said yesterday, if I had z1 times z2 times z3, it would just be 3 r's here, 3 angles there, 3 angles there. Right? So what about z times z? Nothing major there. R squared, because now the r's are the same.
Cosine
2 theta.
Two theta, yeah. So what if it was z times 2 to the third power? R cubed.
So on and so forth.
So of course r as z to the nth power of any complex number.
R to the n
Cosine n theta.
plus I sine n theta.
Kick ass. So what we did yesterday was a little lame because it's easier to just multiply 1 plus I times 2 minus 3i. Just directly, just FOIL the damn thing out. Why would I convert it to this form and then do this rule? So if anybody was thinking that, you were completely justified. But getting here was just a stepping stone to get here. And now if I ask you to do, which I will right now, not by hand all the way out. I want you to try to write it like this first and then do this. If I ask you to do something like 1 plus I to the 12th power. So first try to rewrite that in this form. And remember, how do you do that? What's A and B here?
1 is A, B is 1.
Beautiful. So the angle is going to be easy to figure out, right? Because how do I figure out the angle in general?
Tangent,
Inverse tangent of,
One.
Y over,
in general, B over A.
Yeah.
You guys kind of with me? And this is not new stuff. We're just kind of using old stuff to talk about complex numbers in a new way. But this should feel very familiar. And of course, R,
Is red.
yeah, in general, we squared of A squared plus B squared, so it's easy here. All right, so first try to write it in this form, and then try to attack it with the 12th power.
And you said we do it by the 12th power? Like that one.
Yeah, do it to the 12th power. So in this equation, n would be 12. See, if your R is kind of big at all, R to the n is going to be stupid big. But here I try to keep it not too freaky. Catch up a little bit here. Of course, that's the beautiful one you want to see more often, right? 45 degrees is where sine and cosine are the same, so the ratio will be 1. So if you want to, you can write that as either way. So then from there, it's not too bad, right? Just got to collect that together, and then that's pretty quick to do. A hell of a lot quicker than writing that 12 times in FOIL until you go insane. You go insane about the 7th or 8th time. It's been proven.
Did you go
So
insane?
here, yeah, they have a room full of people that just went insane.
Wow.
So Z in this case, when you go, what's Z for this? Putting all this stuff together, what's Z?
N to the 12.
No, so now 12 powers, what's Z?
Rad 2
Yeah, rad 2,
times
12.
cosine
Oh,
pi over 4
pi over 4, okay.
plus I sine pi over 4.
Kick ass. All right, so that's what Z is. That's how I rewrite a complex number in polar form. All right. So when we first started talking about this, you're like, okay, now we're just playing with shit. Okay, but you know that's what we're doing all the time. So what would Z to the 12th power be, which is really the question?
square root of 2
Square root of 2
times
to the
12.
12th.
Which is 64.
Cosine of
12 times 45.
12 times pi over 4, which is just,
45. What?
what's 12 times 1/4 pi? It's 3 pi, right? Do you guys see that?
Yeah.
Is that nothing major? 12 times 1/4 of something is 3 of those things, right?
That makes sense.
It's cosine of 3 pi plus I sine of the same thing. We stop right there. Does everybody see that? That comes out? It's just 12, because that's what n is, times pi over 4. It's just 3 pi. Yeah, is that good? So now you start to see an immediate purpose, an immediate reason why we might want to be able to write like this. Because that's a hell of a lot easier than it would have been. And yes, sir.
I was just wondering, will these take us back to the identities, I'm guessing, later on? Going to like 2 cosine theta randomly, or cosine 2 theta, I mean.
Not really. That i's in the way for doing anything
Okay.
between the two. Yeah, if we multiply by conjugate, we might get something in short. Or multiply, well, we'll see. I'll do that today, for some reason. All right, so everybody's got this here? No. So what do I get here? Root 2 to the 12th is 2 to the 6th.
Which is,
You guys see this? 64, I like it. And what's cosine of 3 pi? I mean, here's the answer in this form, but now let's kind of work it back to this form. What is cosine of 3 pi? Yeah, it's the same as cosine of pi, right, which is negative 1. 3 pi would be a whole rotation, plus half a rotation. Right, so that's negative 1. And of course, sine of 3 pi is 0. Yeah, so I get negative 64. That's crazy.
oh,
So that's what 1 plus I to the 12th is negative 64. So what is 1, now this is going to be interesting, because this is part we're going to talk about today. What is 1/12th root? So there's 12 12th roots of negative 64. And that statement I just made, this is huge, because this is going to be a big focus for today. Why is that statement true? I'm sorry, Chris, you got it?
Almost done.
All right. So if I had that equation,
There's
It's the
12.
same as the 12th.
then I can take the 12th root. And of course, how many answers should this have? 12. We know that from earlier. It should have that many answers. So 1/12th root of negative 64 is 1 plus I. Because if I take 12, 1 plus i's, I get negative 64. Not a huge deal there, right? Cube root 27 is 3 because 3 3's makes 27. Ooh, it's the same thing here. 12 of these bad boys make this, so a 12th root of this is that. That's not the only 12th root, because there are 11 more. And they're not necessarily 1 minus I, negative 1 plus I. They're not going to be exactly that. How are you doing so far? Is that...
is this where we're getting into the division?
Yeah, so we can do the division now real quick. The division's almost anticlimactic. All right. So if you remember what we did yesterday, let me do this real quick. If I had this, if I divided 2 of these, so it'd be R1 cosine theta 1 plus I sine theta 1 over R2 cosine theta 2 plus I sine theta 2. What do you think you would do with that weirdness? What do you do when you have like 1 plus 2i on the bottom or something like that? Conjugate, I love it. Kick ass. Because that's all I have. I have number plus I number. So I multiply top and bottom by this minus this. Right? R is cool. I'm not going to mess with him. He's fine. So if you do all that, you actually end up getting something. Remember yesterday we just had a brute force multiply this thing out?
Yeah.
Minus I sine theta over 2. And the same thing down there. If you do all that crap, on the bottom you get something. Here's where Jesse's question from earlier comes in. Let me make a point of this real quick. So if I multiply the top out, it's basically the same as what we did yesterday. Except there's a minus in there, right? If I multiply the bottom out, what am I going to get? I get, what do I get? Cosine squared, theta 2.
And then I sine squared.
And the middles cancel, of course. And then minus I squared sine theta 2.
But it's plus.
Beautiful. Minus I squared is minus negative 1 is plus.
Sine.
Cosine squared plus sine squared
Is
is 1. So the bottom just becomes
R2.
R2. Alright. It's funny somebody sounds like they're doing R2. So I get this. I get R1 over R2. And if you guys understand what I meant, this is basically the exact same work we did yesterday, except my identities are going to be difference identities, because the minus that's up there now. So it kind of makes sense. When I multiply R's, add the angles. When I divide, I should divide the R's and probably do what with the angles? Subtract. It only makes sense. And thank God that's actually what we end up doing. I end up getting cosine theta 1 minus theta 2 plus I sine theta 1 minus theta 2. Kind of the reverse of multiplication, which of course division is. So it kind of makes sense. It's nice. If you let it.
We had some type of math last semester to kind of do that. We divided it into subtraction.
Oh yeah, well that's, properties of powers, right?
Yeah.
And I keep bringing this up, and I didn't wear my shirt because I was afraid I freaked Austin out too much. But this thing here, remember this e I pi plus 1 equals 0? I wear that shirt sometimes. So the proof that this and this are really the same, like e to the I theta somehow becomes that. That's really not obvious. It's so desperately not obvious. In fact, you can't even prove that until you get to calculus 2. Right? So one of my calculus students, they could prove that in a week. We're right now talking about exactly what they need to be able to do it. It's really, really freaking neat what these things called power series. But just to kind of make that connection, because this is just a little bit beyond our math, but you can prove that these expressions are exactly the same, which you would never in a million billion years just guess, oh yeah, it's probably the same. And there's no way in hell. It's just a weird circumstance of adding things together, and it comes out to be the same expression that means E. Okay, maybe. And now you can see angles are powers. And that's why I wanted to say that. So when I divide two of them, I subtract the powers. Bam. Right? I mean, that's a beautiful connection. Isn't an angle the power now of E? Mm-hmm. And when I divide two things with the same base, I'm going to subtract. When I multiply two things with the same base, I'm going to add the powers. And the angle is now sort of the power. If you didn't understand anything I said for the last minute and 20 seconds, you're okay. Right? It's a little beyond this. I just wanted to make that point because it's a really good observation that it's exactly like powers. Okay, so that wasn't too rough, was it? No. Especially because the angle was nice. But even if the angle is not nice, if the angle comes out to be 1.178 radians, I don't care. You still do the same work. You just do more of it in the calculator. Multiply it by 12 and whatever. You're doing the 12th power. Not a big deal. Okay. Let's try one more of these before we go on. Yep.
So there can never be at the end of the answer like it leaving in
Just that
cosine
bottom,
or
very bottom.
tangent, like because I remember from last chapter there were certain answers that the result was so ugly they just left it in tangent of blah 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 blah.
I almost understand what you mean.
Almost.
Almost. And a lot of you guys are like, yeah, the same way as you, Jeff.
I don't know how else to describe it.
But let me sum it up. Not really.
Okay,
I mean, go on. It depends on how you want to write your angle. I mean, if your angle is anything that's not a known angle, then there's no real way or reason to write it as anything other than a decimal. Right? Now, if you want to be very, very careful, you would write like inverse tangent in here. Is that what you're saying?
Maybe.
Because, I mean, if I had inverse tangent of square root of 7, that ain't nothing I know, right? So I can just write here cosine of inverse tangent of square root of 7. That's maybe, okay, gotcha. If you wanted to be really careful and not have any rounding errors, that's what you would do.
Okay.
And you can imagine, if I raise it to the 800th power, any rounding error is going to be compounded 800 frickin' times. So at the end, I'm going to be way the hell off.
So where's that bottom? What's that bottom portion right there? I mean, what's it for? Is it this
Bottom portion? This?
Yeah.
This is how you divide any two complex numbers if you put them in this form. The division of two complex numbers would be divide their r's, subtract their angles. which is beautiful because the multiplication is multiply the r's,
Add the-
add their angles. I love it.
add there.
Beautiful.
So,
It's almost
so
too
it'd just
nice.
be, so the only difference would be the plus.
Exactly. There's a minus instead of a plus. It's a divide instead of times. Kick ass.
So how does this play into roots?
All right, we're getting there.
Right. And then
Are we good here?
pluses, yeah, but pluses are when,
Exactly. All right. So let's remind ourselves. This here is this guy here.
And then, yeah,
Thank you so much, Ryan.
you're quite welcome.
Now, the way you kind of figure out roots is you say, okay, what would I have to make if I want to talk about a different complex number than this? I could use Z1, Z2, but here I'm going to use something like, in general, we use, it's really omega, but we'll call it W for another complex number, right? So if I want to figure out the nth root of z, that really means I want to figure out what does a complex number have to be so that when I take it to the nth power, it equals z. What would w then be?
Z to the power.
Z to the
W power? No.
1 over n.
Right.
Come on now. How do you kill at nth power? You take a nth root. Right? And that's what that is. It's the nth root. Square root is 1/2 power. Cube root is 1/3 power. Nth root is 1 over n power. So now, this sounds so weird, what I just said. In fact, many of you probably are like, I don't know what you just said, but what would I have to make W be? So that if I do this to it, it comes out to be just R cosine theta plus I sine theta. Considering, so that's what I want it to come out to be. I want it to come out to be Z. So what would omega, what would W have to be so that when I raise R to the nth power, it comes out to be R?
1 over
No, 1 to the nth power is 1.
1 over n.
Yeah, so it'd have to be R to the 1 over n. What is that to the nth power?
1.
R to the first,
Yeah.
right? So I'm thinking backwards. What would I have to let W be so that when I raise it to the nth power, I end up with this? That is exactly what taking a root is. All right, so what's the square root of 9?
3.
Why? Because that's the number that when I square it, I end up getting 9. So I'm thinking about roots backwards. What would I have to make W so that when I do raise it to the nth power, I do get what I want to get at the end. I get pure Z, right? So I'd have to have R be 1 over n, because then when I raise it to the nth power, it would come out to be R. Right? Let's check it down here as we do this. W to the n would be, it's R to the nth power. And of course, what would that be? R. Right? And then what happens in here, considering that I multiply it by n, what would I have to have here so that if I multiply by n, it comes out to be just theta? Theta over n. And of course, the same thing for this theta. Let me take square root of 9 out of there. Okay. So if I applied this rule to this, it would certainly come out to be that. Think about it. Now let's try it. Let's just do it. So what would W to the nth power be? Applying this rule. This is the rule. What would W to the nth power be? What do I do with this?
Multiplied by n.
Raise it to the nth power. And then what do I do with theta over n?
Raise it to the n power.
No. What's it say to do? Multiply by n.
Oh, this is weird.
And the same thing over here. Multiply by n.
And you end up with that.
And I end up with z. So then W must be the nth root of z, because when I raise it to the nth power, I get z. 3 must be the square root of 9, because when I raise it to the second power, I get 9. Right, it's the exact same thing we're doing, just with a very different thing than a number. Actually, it's a number, but it doesn't look like it. All right,
So
done.
would you cancel those ends?
Totally. So now you can reduce this, bam, so I get R, I get cosine theta, I get I sine theta.
So why did it go from Z to W?
So z is one complex number, w is another complex number.
Okay, I'm talking about right here, black.
This is what z is. This is what z is. And then I'm trying to figure out what would w be to make this true. What would I have to raise to the nth power to make it come out to be z? So that's why I had the 1 over nth power, because then when I raise it to the nth power, I get r. So look at the analogy here. Look at the similarities here. If I multiply, let's see, if I square z, what would this be? Remember, so it would be
R squared.
r squared
Cosine 2 theta.
I sine 2 theta. So I multiply by 2 the angle, and I square the r. So if I do the square root of z,
You get,
yeah, you get r to the 1/2. Let me write it like this. Z to the 1/2. So square root of z, I get r to the 1/2. So I take the square root instead of squaring. And instead of doubling it, instead of multiplying by 2, I'm going to divide by 2. So you see how when you multiply two complex numbers, you add the angles, multiply the r's. When you divide two complex numbers, you subtract the angles, divide the r's. Beautiful symmetry there, right? When I raise something to a power, when I square a cube z, I do that to the r and I multiply the angles. When I take the root, I do that to the r and I divide the angles. Yes, sir.
Does it have to be a natural number? Because I know it can't be 0, but what if it were -2 or anything?
Oh, so yeah.
Just curious because you had n, so it's that normally means it starts at 1.
So if you try to do something like
Z to the -2.
z to the -2,
Yeah.
Well, I meant w to the -2.
or it doesn't matter, whatever complex number you want to talk about. So if we try to apply the rule to it, it should be
R to -1.
r -2.
cosine negative 2.
So this is what it would be. And then we can figure out if that makes sense. Give me a z.
1.
That's true, but something maybe a little more interesting. Let's go back to our 1 plus I. Right? So what's z to the -2?
I don't know.
Square root of
Yes, you do. What does -2 mean? Negative means
1 over
flip it. The 2 means
1 over 1 plus I.
square. Right? So I would flip that, and that one's square. Alright. You understand?
Yes.
We're good? So we can check to see if this is going to work by doing this work. Right?
So that just be then up there would be 1 over all the normalness.
So this would be, z -2 would be 1 over r squared. And this would just be what? Cosine of negative angle. What happens to the negative?
Goes away.
Cosine goes away because it's got even symmetry. And this would become minus.
I.
Right? So to check this, we could say, how would I write this in that form? We did that one earlier. Right? So let's see. In this form, what would this look like? We did that earlier. We got, where'd it
You
go?
erased it.
Root 2 is right there.
Oh.
Root 2 cosine pi over 4 plus I sine pi over 4. So we wrote that in this form earlier. Is that cool, everybody?
Yeah.
All right. So if I do this directly,
So you get red 2.
what do I get? If I do it the old way,
1 over rad 2. Oh, I don't know what you're doing. I'm so confused.
Oh, I see what you're saying.
all right. Let me see.
1
So
plus,
Cardi had a really good question. He said, okay, well, what about negative powers? So let's investigate negative powers. Let's see if this rule holds. I mean, we could try it for a specific example and see if the rule kind of holds. So then the rule would say z to the -2 would have to look like that, just following what the rule says, right? So now let's take a specific example. Let's say z equals 1 plus I, a really good idea because we already did the work for translating it into this form, right? All right, so everybody's cool up to right here?
yes.
All right, so now I'm just looking at it. I'm going to do it two ways. I'm going to do it the old way,
So just
and then I'm going to do it with this rule
It's 1 plus
So
and see if they match.
FOIL that out.
Exactly, yeah, you foil it out.
1 plus.
Plus 2i. Actually, minus 1.
Yeah,
So it's 2.
so it's 1 over 2i, and what would you have to do with that?
Rationalize the
Yeah, so you have to multiply. Well, when it's only I, you don't think about it as a conjugate. You just multiply it by I. Because of course, I times I is negative 1. So you get negative I over 2. Okay, so that's what that is. How we doing so far?
Yep.
All right, I like it. And now we just try it this way. So this is that z to the negative 2 should be 1 over r squared. What was r?
Square root of 2.
So 1 over square root of 2 squared is
2.
good. So 1/2.
Wait, do that again?
So what was r for this? Remember? What was r?
Root 2.
Square root of 2.
Yeah.
So 1 over square root of 2 squared would be 1/2. All right, that's looking promising so far.
Yep.
All right. And then inside I would have cosine of twice, and the angle was pi over 4, right? In fact, I got it right here. So twice pi over 4 plus I sine twice pi over 4. So now I'm just doing this. I'm applying the rule to this form of the thing I'm working with to see if it matches with what we know it should. This one wasn't, the rule doesn't help me. It's easy as hell just to do that.
Yeah.
I just want to see if the rule holds in general, because then I can do like z to the negative 80th power, which I really would not want to do this way. Right? So, what do we get here? We get 1/2. This is beautiful. What's twice pi over 4? Cosine of pi over 2 is?
1.
Cosine of pi over 2 is? That's better. And what's sine of pi over 2?
1.
1. So then I get? I get I.
Yeah.
So it's almost right. Did I lose a negative somewhere?
Yeah,
That'd be awesome.
you didn't make the negative I, or negative I sign.
Minus
Oh,
sine.
yeah.
Minus sine.
Oh, yeah.
Yeah.
Okay.
So you just need to change that.
There you go.
Good.
There it is. And you can imagine, I mean, all z to the negative 2 is 1 over z squared. And then the rule applies to this. Right, so it kind of makes sense the rule should extend the other way too. And sure enough, that looks like it does. Right? We did it this way, we did it that way on a specific example now, but still. And I can't remember if the book makes that point. Yeah, any integer n. Yeah, cool. All right, I like it.
Cool.
All right, so now, where are we here? We got the, and let me summarize what we figured out here. All right, so we know what the nth power does. Let me put right underneath it what the nth root does. And then we'll try to figure out what the nth square root of I is. So the nth root of a complex number would be, the nth root of its r, and then it just divides out. Now, there's one little piece I haven't done yet. Let me fill this in. And to fill this in, let me remind you of something real quick. This is not quite finished.
Yeah.
So let me give you this example here. If we had sine 3x equals, 1. There we go. So now we're taking a little step back.
Take the inverse sign.
So one thing I told you guys, and this is not a bad idea in general, is to not let that 3 freak you out. So let me go ahead and replace that with this symbol theta. Because all I care, I want to figure out what that is first. So now I'm going to solve sine theta equals 1, and then I'll worry about the fact that it's really 3x later.
So inverse sign.
Yeah, so what's theta got to be? 1 sine 1? What angle is sine 1? Pi over 2. Cool. And of course, I would say
Plus.
plus 2 pi k. Then I come back in and say, okay, I really don't have theta, I have 3x. So then what do I have to do to theta?
Times by 3.
No,
Or divide by 3.
Divide by 3. Yeah. So now I'll figure out what x is, right? Cool. And one extra little thing, I think I pointed this out a couple times, but I want to make sure everybody sees this reality. How many answers were there from 0 to 2 pi? Just how many answers were there from 0 to 2 pi?
2. 1.
This is 1.
There's only one place where it equals 1, because it's 0, 1, 0, negative 1. Right, so there's only one answer. So how many answers do you think I'm going to get now?
1.
3. And you should have seen that. Every time that you had to divide, and I asked you to get 0 to 2 pi, you always got a lot more answers than you would normally, right? And I pointed out as we were learning that. So here, what answers would I get? I'm going to get pi over 6 plus, and let me just go ahead and write it as like denominators, right?
Plus 6, 9.
So I would get pi over 6, 5 pi over 6, 9 pi over 6, and the next one would be
Too much.
Too much.
Too much. 13 pi over 6 is outside of 2 pi. It would repeat. It would be pi over 6 again, basically, right? So we would have gotten one answer before, but now we got 3. All right, so just keep that in mind for this next step up here. Not erase that. So what I can do here is I can replace theta with theta plus 2 pi k. Because what I'm doing is I'm dividing that angle by n, so I should actually get n possible answers.
Yeah.
The same way we did here. When I divide an angle by something, I'm going to get that many answers. If there would have normally been 1, now there's going to be n times as many. There's normally 1, now there's 3 times as many. Same way here. Right, so this will be cosine. Like that. And this is true for k equal to 0 up through n minus 1. And think about what happened here. This was for k equals 0. This is k equals 1. This is k equals 2. And the next one was bogus, right? It was outside the range. So we went up to k equals 2, and n was 3. Oh, shit. Alright, so it makes some kind of sense there. I will end up with n answers. Craziness. Alright, let's try this.
Oh, well.
Yeah, it's right there. I love you guys. When you take notes, you don't necessarily have to take... this is on page 560, where they prove this. In the middle of the page, they talk about the values that work for k. So let's see, let's try to do the square root of I. So in order to do this, what do I have to do first?
Put it in that form.
Put it in the right form. So then I got to attack it with that stuff.
Yep.
Right?
Sorry.
That's all right. That's my job. You just help me out sometimes. So what's weird about I, as far as trying to figure out what A and B are? It's not weird, but you just got to be careful. What's A?
0.
0. Good. So 0 plus 1I. So A is 0, B is 1.
So the R's going to
Is 1.
Yeah, so the R is...
Negative.
Oh no, because it's squared, so it's I.
R is the square root of A squared plus B squared. So R is square root of 0 plus 1.
Which is 1.
R is 1. Well, everybody catch up.
I know.
And then the angle is going to be inverse tangent of what weirdness?
B over A.
Beautiful. So the inverse tangent of 1 over 0.
Which is
Beautiful. And what's it about the tangent? Remember what the tangent has on both sides of it?
asymptote.
Asymptotes, which are capturing the idea of what we're trying to figure out. So when does tangent go to infinity? At pi over 2, at kick ass. So this is 1 over 0 freakiness, so I actually get right at the asymptote of pi over 2.
And that's because at the asymptote it's undefined, because it doesn't go past
Beautiful.
it.
So that goes together. Yeah, I like it. Some of you guys might realize, I mean, this is just cosine theta plus I sine theta. So when is cosine theta 0 and sine theta 1? Pi over 2. So you don't necessarily have to fall back to tangent all the time. You can actually figure it out from those two values directly. Or you can fall back to tangent. It doesn't really matter. So how do I write this in the right form then?
What?
Beautiful.
Never mind. Go ahead.
So we got I, we're trying to write I in that Z form, that A, R cosine theta I sine theta form. We got R is 1, kick ass. Cosine pi over 2 plus I sine of pi over 2, right?
Yeah.
And sure enough, it checks out. That's 0, that's 1. I end up with 1, kick ass.
So are we using that top blue one right now, or
No. All I'm doing right now
bottom?
is try to put that into this. Got it.
Normal form.
The polar form. I'm trying to put that I in this form. Because I can't use this idea unless it's in that form.
How do you get 0 plus I?
like the actual.
Oh, so, I mean, y equals 2x. What's the y-intercept?
Well, I don't know.
David's like, don't put me in the spot, man.
And that's called the polar form?
0.
0, because what's there?
Nothing.
Yeah, it would be, so I could put a plus, I could put over 1, I could put a 1. All this crap I could put, but why the hell would we put plus 0? But we just got to realize, oh, it's freaking plus 0. So what, a complex number in general is a plus bi. So if I just see I sitting there, b is obviously 1. A is not quite as obviously 0, because there's nothing
So we're
there.
not even looking at the 1/2 part of it.
Not yet. Because you have to get it in the original form yet.
In order to use this rule, I have to have it in this form.
Yeah.
So the very first part of the problem is get it in that form.
So.
And to get it in that form, I have to figure out what A and B are.
Ignore the one first.
So what is that called? Polar form?
Polar form.
Okay.
Kick ass. Because we're using the polar ideas to write complex numbers. So that's a good idea. That's a polar form of a complex number. All right. So now, once you figure out A and B, you always do the same things with them to figure out the angle and the R. Put it back together. So now I've got I in this form. And now I can do z to the 1/2, like I want to do. So what's the rule say to do?
R to the 1/2.
Good. R to the 1/2.
Cosine of
Theta plus 2. Or no,
No,
pi
theta
over
divided
2.
by
Theta over
2.
Pi over 2
Pi over 4.
plus
2 pi k.
2 pi k
Oh.
over n, which is 2. Because we take a square root here, right?
Yep.
Let me stop there for a second. So all I'm doing is this. I'm filling in everything I know for this situation. So to take the nth root, I would take the nth root of r. Well, r is 1. That kicks ass. I would then divide the angle by n, but I also have to include that plus 2 pi k to catch all the other possibilities. That's what's going to guarantee me. So again, let me come back to this. A 1/2 root. How many 1/2 roots should there be? 2. Because remember earlier, 12th root, there should have been 12 of them, right? So there should be 2 1/2 roots. And how many values of k am I going to use? 0 and 1. I'm going to get 2 answers, right?
Yes.
That's why all this stuff kind of comes back together. I know I should get 2 square roots. This is built to give me 2 answers. Thank God. If it was a third power, I would get 3 answers, like I know I should. Okay. Plus I sine. Oops. Minus I sine. Plus I sine.
Yeah. Negative.
Pi over 2 plus 2 pi k
over 2.
over 2.
Brilliant.
So all I do is I let k be 0, and I let k be 1. I just stop before I get to k equal to the root I'm doing. So if k equals 0, what am I going to get? I get cosine of pi over 4, right?
Yeah.
Which is what?
root 2.
Plus I sine of pi over 4.
Root 2 over 2.
Is everybody cool with that? Because if it's k 0, of course, that piece just goes away.
Yeah.
So I get pi over 4 for both.
So root 2 over 2.
So that is kind of nifty. That's 1 square root of I. If you multiply this by itself, you will get
1.
I.
I.
Because the square root of I is this. So this squared is I. Yes, sir?
Okay.
Just do that again.
Yeah.
Slowly. Do it all.
Yeah.
Right?
Okay, sure.
So we're
Just
Slowly.
go back to get that one.
All right.
so 1 to the 1/2.
Yeah. So are you okay here?
Just do all of them.
Yeah.
Slowly.
Sure.
Better than if you explained it.
So you know,
Go from there.
so real quick, you guys know that I want you to understand this, right? Do you pick up on that? If you don't, that's your problem. But I think at this point you should realize that I want you to understand this. So if I'm going, if up here you're not sure where this came from, and I'm working on this stuff, my God, say something right here. Say, where did that come from? Right? I mean, that's fine. Just tell me right then. We can go back and try to put this back together.
No.
No?
That makes sense.
Yeah, we're-
That
Oh,
makes
good,
sense.
so you are good at
Right.
Yeah.
Okay, all right.
Like that.
And now, what do I let K be?
0.
0
So it equals 0.
or
Or 1.
1. Good. So if K equals 0,
Yep.
I get z to the 1/2 equals, 1 cosine of, well, let's just put it in here. So, or maybe I should put cosine of
Pi over
pi over 4 plus I sine, same thing of course.
Pi over 4.
So I get
Rad 2 over 2.
rad 2 over 2 plus I,
Right.
Rad 2 over 2.
okay. Yeah, correct.
Why or 1?
Because that's,
Yeah.
when I divide by 3, I get 3 answers. When I divide by 2, I'm going to get 2 answers. And there's 2 answers. The 3 answers here were K equals 0, K equals 1, K equals 2. So the 2 answers here are going to be K equals 0, K equals 1, and I stop, because 2 minus 1 is 1. I stop at 1. Yes, sir?
So if it was 3, it'd be 0, 1, 2.
Yes.
Yeah. If it was 18, it'd be 0, 1, 17. Kick ass. Because then how many answers is that? 18. 0 plus the other 17. Cool. But that's why I wanted to do this first. This is a concrete example of it just happening in your face. There are 3 answers here.
Yeah.
Right? I see them. And I can kind of go back and say, okay, that's when we made K 0. Then I added 1 of these. And then I added 2 of these. And then 1 more would have been too much. So that's all this dude is trying to say. Hey, the stuff you did, keep doing it. It's good. It works. Okay. So what about the other answer if K equals 1? Put it up
So
here.
you're gonna-
So if K equals 1, I'll get z to the 1/2. I still get 1 times cosine of, to make that 1, what do I get?
2 pi over 2, so pi.
Pi over 4 plus
Pi.
pi,
So it's
5 pi over 4.
So that's just so then you'll get the right amount of roots.
Yeah.
Because you're including-
So I get all the answers. Exactly. There should be 2 square roots. There's got to be. And I just want to make sure I get all the answers. Cool. Plus I sine of the same thing, of course.
5 pi over 4.
And that's going to be now I'm in what quadrant?
2. 3.
3.
Third, right? A little more than a half rotation. So that's going to be just the same thing, just negative, which makes sense. I mean, what are the roots, the square roots of 9? Not what's the square root of 9?
And-
Yeah, of course. Right? So, because when you square something, the negatives go away. So, of course, another answer would be this same thing, just all negative. Because the first thing that would happen is the negative would die. I get the same damn number again, right?
Yep.
Cool. So it makes sense that I ended up with negative,
Rad 2.
put the I out front. Kick ass. You don't understand what a revelation it was for me when I first learned this. Because I was one of those geeks that early on I was like, what's the square root of I? What's the square root of I? When I first learned I. And my teacher was like, what are you worried about that for? And of course I was worried about it. I wanted to figure out what the hell it was. You give me this I shit, it better do everything else that other numbers do, man. It's a freaking number, right? Even though it's imaginary and all kinds of shit. And sure enough, this is not the answer I would have expected. So I don't even know what you guys were thinking. But it had to come out to be a complex number. A plus BI in that form, there's no way that we would just kind of know it was going to be this. All right, yes, sir.
So where'd you get the names again?
Oh, just because now, once I make K1, I have to add 2 pi over 2 to this. So now I'm at 5 pi over 4. Which quadrant is that? Everything's negative in quadrant 3.
Okay.
X piece and the Y piece.
Okay.
Cool.
Since it's back in complex form, would you try and do the same thing where you put it all up into the...
Oh, to check the answer, you could...
Okay, that you just put it back in a polar form would check the answer?
No, this one I just square that thing directly. Right. Yeah. But there's no other way to get the square root of I besides what we just did. Right? With some of the other work we did, we're like, well, it would have been easier just to freaking multiply the things, man. What the hell? But there's no other way. So a whole slew of things have just opened up that we were never able to do before. You're probably like, well, I was okay with that, John. But no, you weren't.
So this is just whenever you have to divide by the powers, right?
Whenever you take a root.
Right.
Yeah.
So,
Okay. All right, so
does that mean now you can give a z to like the 7
eighth or something like that, or 6.
Yeah, technically I could give you 7/8. You would just do z to the 1/8, figure out all those answers, and then raise each of them to the 7th power. Yeah, I obviously
Or
wouldn't
can
do
you
that.
do it? Can you do
That's
the
a bit of busy work. If I did that, you have every right to come up and yell in my face.
Can you do it the opposite way? Raise it to the
And only if I do
7th power first, and then divide by 8.
Yeah, sure, of course. Because those are interchangeable.
Yeah.
Yeah, I like that. Okay, cool.
Yeah.
Same thing.
Brent doesn't think that way.
All right.
Do another?
Huh? Yeah, let's do another one. Let's do one that's, I is a good one to start with because it's just the more direct. It's like I'm more worried about the square root of I than I would ever be about the third root of 2 minus 5i. I mean, it's just like, man. I don't know if you guys understand what I'm trying to say. I is just so fundamental. I want to know what the hell it does. What's the square root of I? You should be able to tell me, and there it is. All right, so now I can apply this to any other complex number. It's going to become just a process that we use. So let's do one more. Let me let you guys try it out.
This is still 8-3.
Oh, yeah.
Really? This is 8-3 still?
This is 8-3 still.
3's got a lot of information.
So z is 1 minus 2i. Find z equal 1/3. Or they could say find all cube roots of it. Right? Same idea. Of course, you know going in you're supposed to get how many answers?
3.
3. Good. Okay. Just do it this one. Or you just keep it like that if you want to, and just work it out. It's up to you. It's up to you. You can choose which way. Oh, it's just that if you got to be careful if you do degrees, then where we put plus 2 pi theta, you got to put plus 360.
Oh, okay. So radians.
So don't mix the radians and degrees parts.
So degrees, you do 360.
Yeah,
Labs,
you do the degree equivalent of 2 pi, which is
Okay,
360. Yeah.
Thank you.
Sure. And before you guys get too far along in this, if you're doing this, you have to be very careful about what quadrant. I mean, if you graph 1 minus 2i, 1 on the real, negative 2 on the imaginary, right? So you're actually your ass is saved, because when you do the inverse tangent, you will get an angle in the 4th quadrant. But if I would have put negative 1 plus 2i, you wouldn't want to use that. You should be in the Second quadrant then, right? You have to be careful about your quadrant when you do inverse tangent. You always have to. So you get the right angle there. Yeah. Oh no, it's plus. I think I put a minus there for once for some stupid reason. Yeah, it's still a plus here. Right?
Okay, so
Still plus there. Yeah, I think at one point it would become negative if I had a negative inside. I could take it out. That did happen once today. Because the sign of a negative would be a negative sign. So you got to come out pretty, but it's really just an exercise in are you able to plug stuff in the right place? Are you able to follow what the rule says to do?
Yeah, no, that's the level.
When would you want to round? I mean,
Well, so there's the earlier question. It depends on how precise you want to be. So if you really want to be precise, you just throw that in there until the very end.
storyline tag.
Yeah, exactly. So you can do that. You can do like a memory store because the calculator has more decimals than it shows. Right? So you can either write it like that in the expressions and then throw the whole thing in the calculator once at the end, or you can store it in memory. But for right now, we can just approximate it. It should come out. It's only a cube root. The larger the root, the more the error gets compounded. as I look at so far. Is that what you guys are getting? Yeah.
Yeah. Well,
Yeah,
I did the whole
that's what I
tan
got.
thing.
0.
And from here, you just put in the calculator.
Yeah, now you do k equals 0, k equals 1. So, I mean, really, you guys should be able to handle, instead of just putting that in there, you should be able to handle just put that in there. You're just going to plug the damn thing in your calculator anyway, so what's the matter what buttons you're pressing? Or, like you said, you can just,
Store it.
like, you could just store that number in memory, or in like X, and you just put an X there. Not a big deal. Alright, so if you don't want to have any rounding errors, you can just do that. It's a really, really fundamentally just a plug and chug exercise, truly.
I don't know what that means.
You got the minus. Yeah.
Oh, that's funny. Oh, okay. You're that's fine. So you got it in complex mode. Right?
Yeah. Well, I use the eyes.
Yeah.
What the hell's where's that mode?
What's up? It's a general mode. You turn it on or off. So you have an I button.
Yeah, I use my eye button.
It's not a bad idea. I just didn't necessarily want to talk about it. But there's an I down there at the bottom. The more industrious amongst you might actually find it and use it.
I don't know what that answer means, but it's all right.
That's what it would be. That's A plus BI.
Oh, it's just the negative. Oh,
A
minus. I got it.
B is
Okay.
negative. Yeah.
I got it. Makes sense.
Yeah.
What's up? How we doing?
You hit I where you would use.
Yeah, there's an I right there. Right? Any way to check your work? So if k equals 0, you get 5 to the 1/6 times cosine of inverse tangent of -2 over 3 plus I sine of inverse tangent of 2 over 3. All right, so let me just do that one, and the other two are just plugging in a couple of extra things in the calculator besides that, right? If you go k equal 1, then k equal 2. I know that's where I stop. So if we do this in the calculator, I get, so we can with that 5 to the 1/6?
Yeah.
Pretty good. Times, let's see, cosine of inverse tangent of -2 divided by 3. Oops. I love all the parentheses. Plus, oops, got it. Bam. And what's really nice is I can just hit second enter. So what you guys got for the first piece?
You can leave I out, right? You just put that.
Yeah, leave I out for now. Because you just wanted to get the A and the B, the coefficients for the real and the imaginary parts. So if you do this, just hit second enter, replace cosine with sine, I get that. Is that matching up with what you guys got?
No, but I did something wrong.
Let me try this again. Times.
So what's up? So 5 to the 1/6 times cosine of inverse tangent of -2 parenthesis divided by 3.
Wait. Oh, okay.
So just make sure you know that parenthesis is closing the parenthesis there, and that parenthesis is closing the parenthesis there. Gotta love all the parentheses. So one answer would be roughly 0.195
Yeah.
minus 0.39i. That's one possibility. And let me just show you how the I stuff works.
Where's the 5.195?
Because that's what I got. So when I put this in the calculator, this here, 5 to the 1/6 times this, I got 0.195.
Okay.
I'll make sure you're in radians, right? Okay. So yeah, that's where it came from. And then when I put that in there, I got negative 0.39 roughly.
Oh, you do them separately.
Yeah, definitely. Yeah. To check this, let's try this out. So if I put in there 0.195, minus, that's not going to come out perfect. I just want to see if it's close. Minus 0.39 I. So there's your I button. And of course I'm going to raise it to what power?
1/3.
Not the 1/3. I'm trying to
Oh,
check
so
the
the
answer. I'm
third.
going to cube it to see if it comes out.
Something different.
Let's see what it comes out to be. Weirdness.
Yeah, I think isn't the tangent of -2 supposed to, the divided by 3 supposed to be in parentheses?
Oh, yeah. That should be dividing the angle. That's right. That's my bad. So it should be theta over n. I don't know why I wrote it.
Holy
Where is
crap.
that coming from?
There you go. So in the, do I have it up here? Yeah, in the formula, the n is inside, right? That's my bad. So we just put that n inside. Let's see if that matches up better. What you guys got? So right here it should be inverse tangent of -2 over 3. Because it should be theta over n inside. Cool. I just wrote it down. So 1.09.
Yeah.
Is it better? So 1.09 minus, and now we just replace the cosine with psi. Get -0.73. So real quick, if I try to check that, so let's see what I got here. I got 1.09, and it's minus 0.73.
5.
I'm still getting much different.
It's not quite. Well, it's a little, that looks good. Minus 2i. First part definitely needs some work. It shouldn't be that far off. Alright. Still got some prices in the wrong place. Yeah.
Can you look at mine and see where I'm messing up?
Oh, you're fine. You're fine.
Then why is mine so much different?
Yeah. I think I had it in the right place before. I just.
I think you,
So
because
this is the angle. This is theta. And it should be over 3.
3, yeah.
Yeah, I think I just had parentheses in the wrong place. Well, let me show you one thing. This is, we'll do a better one next time, but I want to show you real quick. We're going to get into the math behind graphing things like this here. No?
Because that's different.
It looks a butterfly.
Yay! So you watch this for a second. Actually, yeah. Okay. It's kind of cool. And let me show you the equation behind this. Yeah, just can't let it keep rotating through all its values. That's kind of cool. I don't know if you ever watched Venture Brothers, but I was tomorrow.
Just keep going.
Yeah. So that's the equations behind it.
So what's your final answer for that?
Well, we gotta keep working on it. I kept having my 3 kind of in the wrong place on there. So it should be cosine of this divided by 3.
1.219.
Yeah, 1.219 minus
Blah, 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 blah.
1.479.
Yeah, okay, I did it right the first time.
So we'll do another one of these next time. Maybe I'll try to make the numbers come out nicer for us. Sounds right. We're done with 8, basically.
Okay.
Yeah. And that's 8-4 is the butterfly.
Oh, that's it. Okay.
So, I was looking at this, and that's just because it's in the wrong quadrant, yeah?
Yeah.
And that was all it was. It was just because I wasn't looking at the...
Yep. It's in the wrong quadrant.
I just wasn't looking at this stuff. The negatives here.
Exactly.
That's
Where is it to begin with?
And
It
so,
better still be there.
basically I was finding the reference angle, and I needed to put it in the right quadrant.
Exactly.
Okay. Oh, and then, yeah,
We're doing
last one.
tan of -2 divided by 3 now. Tan.
Yeah, exactly.
Okay.
That's what I had.
This is all in radians, right? You were saying this is radians.
Total.
Okay.
Yeah. Because when you see that, it's got to be rated.
Yeah, well, I don't know.
60
I
there.
just, when I was trying to do the whole thing, it was coming out different. But I could just do this. multiply
should
by,
be
and then
1
multiply.
minus
Yeah, so it should be 1.22 roughly.
But I can break it, I don't have to do that. Or I could, okay.
I need to rework the section down.
The second one is 0.272.
Oh, see, I know.
So you finish the one out.
Oh, sorry.
Correct, and then 4.7.
There's 4.719, yeah.
Okay, well then you put those into the calculator and you cube them. Yeah.
Beautiful.
I get that 99 minus
What
1.9.
would our tangent theta be? It's not defined to me.
You cube all of them.
What's tangent theta?
You cube all of them, right?
Yeah.
So, consider that.
You remember how they, so you have, r squared is x squared plus y squared. Something theta is, tangent theta is,
Little letters.
get that?
Yeah, no, definitely.
That's what tangent theta is.
I don't know.
It almost seems too easy, but if you know that this is true, and you're converting, if you see tangent theta, make it y words.
Okay.
It's only the sine and cosine that needs an r, because their definition is r sine theta is y. This is straight up, there's no r needed, it just equals that. Cool.
See what I did there?
Oh yeah, that was so weird to me.
I know I was working too fast. I didn't do 180 minus that minus that. That's the only thing.
Oh, I see, okay.
So I did 110 minus that and get that.
Okay,
I was working fast.
Yeah.
And the only other thing was you thought that I didn't carry the negative, but I tried to represent that without having to do that, so I could really sign. I did it kind of in my head.
Oh, I see with that. Okay. I see. All right, I give you one more point. Well, you could have gotten 11 points.
So I could have got. Can't you replace your test score, replace your quiz score?
Oh no, so I never update that here, and that's why Ryan was saying you would see that on the grade sheet summary when I give it to you. I do it in the computer.
Yeah.
If I try to go back to every quiz, screw that.
Okay.
You'll see it in a grade sheet summary.
Okay.
Yeah, it's in the computer. Your bar in here. Real quick. Let me see. Make sure I remember to do this. Oh,
Thank you.
take that away. Thanks, man.
Okay.
Hey, this is still on.
I don't have a stapler.